the roads over here in Fiji. It has 18 buckets, each holding 15 cubic meters of material. And if you can understand, a 20-foot container is about 33 cubic meters. So there's got 18 bucket wheels. So that's like 9 20-foot containers worth of material it can extract every time it spins that wheel through 360 degrees. That's pretty phenomenal, right? Now, why am I bringing it up? Well, because the same methods that you use to calculate the tension in cables in the very simple problems is the same methods that we use in the most complicated problem. Yeah. And at the end of the day, all of the forces have to track through into the base and into the support arms and into the truss structures. And so trying to tie it in all together is the things that you learn in the very basics is what you'll apply in the more complicated scenarios. And what we're always trying to do is trying to bring very complex things into very simplistic ways to analyze it. Okay. And eventually you'll learn things like finite element modeling, where you do very complex things within a computer simulation. And that's what I do for a living when I was at Boeing. So I just wanted to give you some context there. It looks very simple here, but the same things that you do here get applied in very complex scenarios. Yeah. Okay. So the objective for this chapter is to investigate the forces on particles. So replacing multiple forces acting on a particle with a single equivalent or resultant force. Okay, so we can have multiple forces acting on a particle. And that's good for seeing how load gets transferred through a single point. At the end of the day, when we want to analyze that single point, we can resolve it into a single resultant force. Relations between forces acting on a particle that is in a state of equilibrium. Remember, whenever we're talking about equilibrium, I'm talking about some of the forces in the x equals 0 and positive to the right. Some of the forces vertically in the y direction equals 0, and some of the forces, well, it's funny with z equals 0, but I'll say it's coming out of the page equals 0. That's our translational forces, and then we've got our rotational forces, positive counterclockwise. Some of the moments about the x equals 0, some of the moments, moments about the y equals 0, and some of the moments about the z equals 0. These are our equilibrium equations, okay? These are equations which will form the foundation for your mechanics journey, and you're never far from these, yeah? Don't forget them. I want you to remember them. The forces on particles does not imply a restriction to a minuscule body. It's like I was saying, it's not about an infinitesimal body. It's about the study of we're restricting the analysis to the size and shape of bodies under consideration. So, for example, we can have a car, and I'm going to draw I'm actually a good artist, actually, but anyway, not with this pen. So I've got a car. We've got lots of things acting on this. We've got friction. We've got mass. We've got passengers inside. They've got their own mass. We've got drag acting on it. Okay. And then we've got the torque acting on the tires. Now, all of this can be simplified to a center of gravity, essentially a particle with mass, drag, and then we've got all of our additional things like friction. So a force down here is an eccentric load, so we can have torques acting on there as well. Okay, so that's what I'm considering here. Yeah, forces being applied or assumed to be applied at a single point. So we've got something complex being distilled down into something simpler to understand. Yeah, correct, Rohan. Weight equals mass times gravity. Okay. So in this case, we've got the mass here multiplied by gravity would be equal to the weight. Okay. So here are, well, let me just make sure everything's expanded. The resultant of two forces. So a force is an action of one body on another, characterized by its point of application, magnitude, line of action, and sense. Now, this definition here of a force is very similar to what we would call a vector. Yeah, this definition. Yeah, it's very similar to what we would call. It appears to be anyway. So here we've got a direction, we've got a magnitude, we've got a sense, and we've got a point of application. Okay, so this is a force. Experimental evidence shows that the combined effect of two forces, so now we've got two forces, may be represented by a single resultant force. The resultant is equivalent to the diagonal of a parallelogram which contains two forces on adjacent legs. Sense is direction. Yeah. So the sense of this force could be, well, it could be tension, it could be compression, but I always say we've got the point of application, we've got the magnitude. This is the magnitude. Magnitude. We've got the line of action. The line of action is this dotted line. So line of action. It's a line that extends to infinity. Yeah. And it passes through the point of action or the point of application, and it goes to infinity. And then the sense, Dwayne, is the hey, which way am I pointing? Okay. Great. So so over here we've got the resultant of an equivalent to the diagonal. The resultant is equivalent to the diagonal of a parallelogram. So I've got two forces here, P and Q. They both act through point A. What we're saying here is the resultant, R, is equivalent to a parallelogram. So essentially I've got Q here and I've got P here. If I were to draw a line parallel to P from the end of Q, I would have this dashed line here, and I'd call that, let's just call that P prime. And Q, if I were to draw a parallel line to Q, extending from the end of P, I would get Q prime here. Okay, now they form a parallelogram. Q prime and Q are equal. P and P prime are equal. Where Q prime and P prime intersect, I can draw a line from A through to this point here. Let's just call that F. And I have the resultant force. Okay, so this is essentially the parallelogram rule, which says that Q squared, the sum of Q squared plus P squared plus Q prime squared plus P prime squared is equal to R squared plus another one here, and let's just call S, is equal to the sum of the squares of the diagonals. Okay, so that's the parallelogram rule. If I were to just distill it down to something, it's a visual rule, or it's a graphical method for determining resultants. So if you had set squares and rulers, you could simply find out what this angle is here between P and the horizontal. You can measure that angle. I would come to the end here. I'd measure that angle again. And so if that was angle theta, this would be angle theta, and I would draw a line. Okay, I'd come in and do the same thing for Q. I'd come in and measure this angle here, and that could be angle phi. I'd come, extend a line here. This would be angle phi. and I can draw this line. Yeah, so I can draw Q prime like that, and I can come in here and draw this guy, that. Oh no, that's terrible. Anyway, what I get is the intersection of those two lines. Where I get the intersection, I'm then able to draw the resultant, and there's my resultant. Okay, so that's the parallelogram rule. Let me just keep moving. Any questions there? We're good? Force is a vector quantity, which I explained up here again. Let's go on here. So vectors, parameters possessing magnitude and direction that add according to the parallelogram law. So examples are forces, displacements, velocities, and accelerations. Sorry, can you just please mute your microphones? Everybody, please mute your microphones. It's very distracting. I don't know who it is.
Securely with your phone, microphone, please.
Thank you. Thanks, guys. It's hard to keep your train of thought when you got all this noise coming. Okay. So here we've got vectors, okay? And scalars are parameters possessing magnitude but not direction, okay? Examples are mass, volume, and temperature. So vectors classifications, fixed or bound vectors, have well-defined points of application that cannot be changed without affecting an analysis. So when we're talking about forces acting through a point, you can't just remove that vector from its point of action. You're going to effectively change the moment, or you're going to change the total. Well, you're not going to change the total load acting, but you'll definitely change the moment being applied. Free vectors may be freely moved in space without changing their effect on an analysis. Sliding vectors may be applied anywhere along their line of action without affecting the analysis. Okay, so sliding vectors, they can slide along the line of action. Free vectors are vectors that are open in space, that are moving around without changing their effect on the analysis, okay? We mostly work with fixed or bound vectors, yeah? Sometimes with sliding. Free vectors, not so much. So addition of vectors, this is important stuff for you guys to remember, especially if you get asked the parallelogram or triangle rule, which visual means. So up here on the left, and I just covered it slightly, was the parallelogram rule. Yeah. Over here, we've got the triangle rule. We also have, so with the triangle rule, essentially we displace either one of these vectors, either Q, you can displace Q, or you can displace P. So I shift Q from point A and I put it to the tip of the vector P, and then the resultant is P plus Q. P plus Q can also be achieved by moving P from its line of action to the tip of Q, and I get P plus Q as well. So you can see that vectors are commutative, yeah? We also know that vectors follow the law of cosines. So the resultant squared is equal to P squared plus Q squared minus 2PQ cos B, B being this angle here, okay? We also, oh, sorry, I've got to clear that. We also know that it follows the law of cosines. So when I'm trying to work out some of these problems, I use the law of sines and cosines. If I've got, just to be clear on this, so I've got here, I've got A, I've got B, and I have C. So sine of A is this angle in here. Sine of B is this angle here. And sine of C is this angle here. So if I know one side, if I know two sides and one internal angle, I should be able to use the law of sines as well as the law of cosines. Yeah. This, for the law of cosines, you need adjacent sides of B. Okay, so you need this internal angle plus Q and P. Okay, and then you can work out the resultant. This shouldn't be anything new necessarily. You should have probably covered this in your physics or your maths at high school level. It's just maybe a new application, I don't know. Remember, vector addition is commutative. So vector P, sorry, just to be clear, this is also our notation for vectors, yeah? It's got a little hat over the top, so it's P plus our little arrow, yeah? And then we've got magnitudes, so AB, got AB hat, which denotes the side or the length of that side AB, okay? And vector subtraction, so if Q is in this case, if we've got a Q that is negative, it's just in the opposite sense to the original Q that was given. And so P minus Q is you flip the sign or the direction of Q, and that would give you vector subtraction. Now we've got the resultant of several concurrent forces. So concurrent forces are forces that pass through the same point. So in this case, we've got point A over here that has three vectors, 1, 2, and 3. They all pass through the same point. Now, when we have this, we can add them all tip to tail. And it doesn't matter which way I do it. I can have P plus S plus Q. We could do it like that. We could do it like this, Q plus S plus P. But you can see that any way that I do it, I arrive at vector R. Okay? That just goes to show that it doesn't matter, as long as you understand the rules of vector addition, that you can add them in, well, it's commutative, right? So I can put them in different orders, but I should get the same resultant, yeah? So let me just keep going. Vector force components, two or more force vectors that together have the same effect as a single force vector. So in this case, you see I've got Q and P has a resultant force F. Over here, Q plus P is force. So it's just saying that what I can do is, instead of adding singular forces together, single vectors, I can sum them together and simplify my problem so that I just have one resultant force acting on the body. And they will have that one resultant force will have the same effect as the other two. So here we have a sample problem, okay? Now we've got two forces acting on a bolt at A, and it says determine their resultant. So how many of you would be confident to be able to do this problem? Do we have any? Dwayne, you could do it. Good stuff. One person out of 215. Sulueti, awesome, awesome. Nice, Nitesh. Good stuff. Rashan's volunteering. He wants to do it. Okay, so remember when we have this, the strategy is, let's have a look at a graphical solution. Construct a parallelogram with the same direction as P and Q and lengths in proportion to these forces. Graphically evaluate the resultant that is equivalent in direction and proportion in magnitude to the diagonal. So the trigonometric solution, we can use the triangle rule for vector addition in conjunction with the law of cosines and law of sines to find the resultant. So there's a number of ways we can skin this cat. The other way that we can do, and we haven't done this yet, is we could also even resolve Q and P into horizontal and vertical components, add the corresponding horizontal components and vertical components, and then use Pythagoras theorem to extract the resultant. Yeah. So not, for the most part, you will not be doing. it's a good it's the parallelogram rule and the triangle rule. Good graphical means and trigonometric solutions, but typically you won't be doing that. Especially when I do things like in Excel, I always I'd be breaking Q down and P down into X and Y components and then adding them together to get my resultant. Yeah. So that's how I would be doing it. Here we go with modeling and analysis. So we've got the graphical solution, a parallelogram with sides equal to P and Q are drawn to scale. The magnitude and direction of the resultant are measured. So here, we've got P and Q. Remember, there's a number of ways you can do it. In actual fact, you could even use a compass. So you can come in and measure this length Q over here. And then with the compass, so you have your compass. Okay. You measure Q, then you bring that compass and you can put it at the tip of P and scribe an arc. Yeah. You can do the same for Q. You can bring in a compass here, measure that length of A to P, and you can come over here and scribe an arc. At the intersection of those two arcs, I can then draw a line from A to P, A to the intersection, and I would have my resultant. And then you would measure it because you'd have to do it to scale. And if you do it to scale, you'll end up with a resultant of 98 newtons and an angle of 35 degrees. Yeah. Is that clear, guys? Is that clear what I've shown you there?
Yes, sir.
Okay, great. Just want to be sure. Okay, and then the next one, the next one is the graphical solution using the triangle rule. So here I've got Q and P, and they both have a line of action at A. Now what I want to do is I want to displace Q and put it at the tip of P. Once I have that, I can then draw my line of action for the resultant, right? From A through to the tip of Q as it's displaced, and I get R. So that's the other graphical means that you can do it. Again, you probably, if you did it, you'd probably have to get your protractor and measure that angle. That angle, I think, was it 25 degrees? I can't remember. From the previous slide, you'd measure these angles. That you've got that angle, you measure that angle, and then you can draw a line that is equal to magnitude of Q. And then when Q ends, I can draw my resultant. Okay, so that's the other way to do that. And then lastly is the trigonometric solution. Yeah, Mark, how do we find newtons? So newtons is force times acceleration, mass times acceleration. So it's kilograms times meters per second squared, which equals newtons. So when we're talking about mass, it would be, for example, I would be exerting, let me just write. I would be, if I were a particle, I have mass of 95 kilograms. Let's just say 100 kilograms, just for ease of calculation. So didn't think of that well. So just say I'm 100 kilograms. The gravitational constant is 9.81 meters per second squared at sea level. So then weight, which is also equal to force, would be equal to 100 times 9.81, which equals 981 newtons. Okay, or short is newtons. Kalani, are you apply of? What do you mean, bro? Cosines. You want me to show you how to apply cosines? I don't have one here. Well, yeah, we could apply cosines here actually, and it has been applied in this problem. But the other way you can do it, if you don't have a set square and you know, your tech drawing equipment, is you can use the trigonometric solution. So we can apply the triangle rule from the law of cosines, or we can apply the law of sines. So this is what we do know. So if we go back, if I go back to the original problem, we know the angle between Q and P is 25 degrees. Yeah. So we know the angle between Q and the horizontal is 45 degrees. Okay. So now we've got the trigonometric solution here. So we need to draw this together. So we have B, which acts at an angle of 20 degrees. Then we know that the line of action of Q is 25 degrees offset from the line of action of P. So you can see here's the line of action of P. So now I've got 25 degrees between that line of action and Q. So I extend it. And we know that that's 60 newtons. This is 40 newtons. And so I can draw the resultant. And all of this doesn't have to be to scale. Okay, this can be just done on a piece of paper, just like I'm doing, you know. So I could come in here and I can just write, oh, there's A. I draw to point B, and this angle here is 20 degrees. Then I come in here and I know my line of action of P is there. So I draw Q, and that is 25 degrees. Okay. And then I'm able to draw my resultant. And that's what I need. So now I need to work out some angles. I know this is 25 degrees. And then from the line of action, so this angle all the way across to the line of action of P must be equal to 180 degrees. Yeah. So therefore, the internal angle B is equal to 180. Sorry, I drew too many things there. Is equal to 180 minus 25 degrees, which equals 155 degrees, which is this internal angle here. Yeah? Is that clear, guys?
Yes, sir.
Great. So now I know a number of things here, right? I know Q is equal to 60. And I know P is equal to 40. So I know two sides and the internal angle 155 degrees. So now I can use the law of cosines over here. Yeah, law of cosines. So I know what P is, I know the two adjacent sides, and I know the internal angle B, which is between those two sides. So then I can work out R squared is equal to 40 squared plus 60 squared minus 2 times 40 and 60 times the cos of 155, and I get my resultant, 97.73. Yeah? Now, once I have that, I can then work out my internal angles as well using the sine rule. So the law of sines. So now I have my resultant here, and I have my internal angle 155. So these two are, this is the resultant is opposite 155, and I have 60 degrees, and that is opposite this angle here, right? So in this case, we're calling that A, okay, the internal angle A. So I have sine A over its opposite side, which is Q, is equal to sine of B, which is 155 degrees, over the opposite side, which is R. Now I can rearrange for sine of A, and I get sine of A, well, I get A is equal to 15.04 degrees. Now that's the internal angle of that triangle. So therefore, the line of action of the resultant R with respect to the horizontal is equal to alpha, and alpha is equal to 20 degrees. Is equal to 20 degrees plus the internal angle A. Yeah, Dwayne, it doesn't always have to be to the horizontal, but because the original problem defined all of the lines of actions of P and Q with respect to the horizontal, it's better for you to put it within that system, yeah? So sometimes it could be with respect to the vertical, but it really depends on how it was framed in the problem, in the question to begin with. Yeah, Valraj, the angle A, yeah. So so remember, we've got all of this. Up here, this is the angle A. It's just the internal angle. This is the angle C, and this is the angle B in our triangle, okay? Sorry, that looks like 6. B, C. Okay, so when the law of, as it relates to this triangle, the law of sines says sine of B over R is equal to sine of A over Q is equal to the sine of C over P. Yeah. So if I know 3 variables, if I know R, I know B, and I know Q, I can solve for sine of A. Right. Same thing. I could also, if I had C, sine C, I could do that as well. Does that make sense, Valraj? Sorry, I'm just seeing messages coming up. No worries. Okay, I think I've got one more problem here. Okay, sample problem 2.2. A barge is pulled by 2 tugboats. If the resultant of the forces exerted by the tugboats is 5,000 pounds, so now this problem is giving us the resultant, which is 5,000 pounds, directed along the axis of the barge, determine the tension in each of the ropes where alpha equals 45 degrees. Okay, so let me just expand on this. So we've got a graphical solution and we've got the trigonometric solution. Okay, same thing that we did before. Now, I'm just going to draw on here some important things that we need to know about this problem. It's giving us, straight away, it's given us the resultant. Okay, the resultant is 5,000 pounds, right? 5,000 pounds. Okay, and that is being directed along the axis of the barge. So we're assuming it's horizontal. So it's, if you can see that 30 degrees, that horizontal line, that's the axis of the barge. Okay, so I got 5,000 pounds. Now, and the tension in each of the ropes is alpha is 45 degrees. So that is equal to 45 degrees. So now I can solve this. I can solve this quite easily. So I'm going to just go for it using the triangle rule. So the triangle rule says that rope 2, which is from B to C, is acting at 45 degrees. Okay. So that is 45 degrees in here. Yeah, and that is vector BC. Okay, and the other one is here, and that is 30 degrees. And that is vector BA. Yeah. So if that's 30 degrees, that's 45 degrees. And 45 and 30 is 75 degrees. So this must be 105 degrees. Yeah. Now, straight away, I mean, I know I'm using the trigonometric rule here, but straight away you can see I can use sine rule, yeah, to determine the forces in each of my ropes. Yeah. So I have sine of 30 degrees on BC is equal to sine 105 over 5,000. So then I can solve for BC. BC, the vector BC, is equal to 5,000 times sine of 30 divided by sine of 105. Okay, so now I've got BC. The other one I have is I can do for BA. So sine of 45 over BA. No, it doesn't matter, Nicole, that we're not in newtons, it's just in pounds. So your solution will come out in pounds because it's just degrees or radians and pounds, so it's not going to matter. As long as you remember that you're in pounds. Okay, so BA sine of 45 over BA equals sine 105 over 5,000. So therefore, BA is equal to 5,000 times sine 45 over sine 105. And I've got the two components, 1 and 2, which are the tension in each of the cables. Yeah. Now let's. Yeah, so the other thing that you can do is you can do the triangle rule or the parallelogram rule, Nitesh. And again, remember the difference with the trigonometric rule, which I just showed you, is you don't need to draw the drawing to scale. You don't need to take measurements. You don't need to worry whether you've got the scale right or anything like that. It's just using mathematics to solve it, yeah? Whereas the parallelogram rule and the triangle rule, you'll have to make sure your angles are measured correctly. If you're out by 1 degree, so just say instead of measuring 30 degrees, you measure 31 degrees, well, you've automatically increased the length of vector BC. Yeah, and if you make it shorter, if you make that angle 29 degrees, you've reduced BC as well. Okay, so there's things that can go wrong when you're doing the trigonometric, when you're doing the parallelogram or the triangle rule. So let's go through and see how we solve it. So here is the parallelogram rule. So, the parallelogram rule is we know that we've got the 5,000 pounds acting along the horizontal. Okay. So you would draw the 5,000, okay? Then what you would do is you would draw lines of action, Yeah. So you draw the 5,000, then you draw lines of action of T1, 30 degrees, and lines of action of T2 at 45 degrees. So you would draw, let me just put it here. You would draw a line of action of T1 like this. You draw a line of action of T2 like this. Then what you would do is you'd go to the tip of the 5,000 because that's the only vector that you know the length of, 5,000. And you draw a line of action of that, 5,000. And you draw a line of action. And remember, I'm doing 45 degrees, right? So it has to be a line that's parallel to T2. And then over here, you've got to have a line that's parallel to T1, okay? And I draw a line of action from the tip of the 5,000 through to here at an angle of 30 degrees. And I would get the intersection. Where these points intersect, those are the individual tensions in each of your cables, in each of your ropes. And then I can draw, hey, no, I don't want to draw that. I want to draw this. I can draw T2 and I can draw T1, yeah? So how do we know that the angle is 45 degrees? Remember, at the start of the problem, it says alpha is equal to 45 degrees. Okay, so it's given right at the start. Thanks, Nico. Yeah, it's given at the start of the problem. So this is equal to 45 degrees. It's given right at the start of the problem. So that is, that's the parallelogram rule. And then once you've got that, you would come in with your ruler and you would measure. You would measure this and you'd measure this, and it'd be to scale, and you'd transfer that into a force. It will be always given? No, it won't always be given, Rohan, but it's the only way that you can solve this problem. So the person that, the architect of this problem knows that you require that 45 degrees. If you're not given it, then you're not going to be able to solve that problem. Now, in the real world, you're probably not going to have this. You're going to have to think of ways and means to measure these angles and measure these tensions. But again, this is getting you to think outside the box and give you tools to be able to solve these kinds of problems. Okay. So then, can we separate the two triangles and find the tension in each? So they are linked together. So if, yeah, sorry, let me just answer Rusi's question. Can you separate the two triangles? No, because they're connected, right? They form a system. Yeah, remember, they produce the resultant force, 5,000 pounds. You can't go and analyze the alpha triangle without analyzing the 30-degree triangle. Dwayne, sir, so if this comes to the exam, would you use graphical? It depends on what gets asked. Okay, if you get asked this, you're going to have a protractor, you're going to have a compass and set square in order for you to answer the problem. For me, I'd be going trigonometric, right? But I don't know who's setting the exam. Of course, I know who's setting the exam. So the trigonometric solution is the one that I'd already discussed earlier. Okay, so the trigonometric solution is, you know, you've got the 5,000 pounds. You then draw your T2 or you draw your T1. Yep. And from that, you know your internal angles. And then once you've got your internal angles, you can use the law of sines to be able to solve the problem. Yeah. So I already did this one on the previous slide. Yeah, you'll have some rounding errors. If you did it in Excel, you probably wouldn't have any rounding errors. It's 2588. Yep, it's probably rounded. So let me do this in Excel and maybe. And maybe we can see what we're doing here. If I take this, you just take this, copy it, and paste it in Excel. So I've got my reference, and yeah, you might have to scale it down, Russi. So 5,000 pounds, maybe that's 5 centimeters. Yeah, or maybe that's, yeah, maybe that's 5 centimeters or 5 inches or however you want, right? Okay, so if I share my screen with Excel, so this is the Excel problem here. So we'll use just sine rule. So I just say sine rule. Now remember, in Excel, it doesn't deal in degrees, it deals in radians. So let's just have angle A, B, and C. So angle A is in degrees. Let's just say degrees and degrees. The angle A, oh wait, do I have A? No A or whatever, is it? Okay, we've just got 30. We know B is 45, and we know the last one is 105. In Excel, your sine equations, cosine, your trigonometric functions are all done in radians. Okay, so you can't just type in, if you go equals sine of 30 degrees, you're not going to get the right answer, because you know what the sine of 30 degrees is, right? The sine of 30 degrees is a half. Yeah, so we know that we're wrong straight away. So now I've got, let's just put sine of these angles, sine, sine, sine. So sine of A, sine of B, and sine of C. Oh, it always does that. Sine of C. And we have to convert it into radians. So we would go equals sine of radians. So I'm calling out the radians function. So it's going to change my angle from degrees into radians. So I can use the sine function. And look, I get a half. Now, once I've done that, I can just drag, I can click on the corner box and I can drag it down, and it gives me the sine of all these angles. Yeah. So that's sine of root 2. Or sorry, it's root 2. So now I've got my length. So if I've got sine of that, the length, A, B, and C, we've got to look at the sides that are opposite. So the angle, the length opposite 30 degrees is, what do I have? I've got T2. Well, I know what the one opposite 105 is, right? The one opposite 105 is 5,000 pounds. Yeah. And I don't know what these two are, but I can work them out. Yeah. So what I had before was sine of, oh, I can write it on this screen. So that, oh, what did I just do? Just unshared it. Okay. So what I have, can you please mute your microphone, Jamil, whoever that is? Okay, so then I have A, the vector A over, actually I think it's T2. So I have T2 over sine of 30 is equal to 5,000 over sine of 105. So therefore T2 is equal to 5,000 sine 30 over sine 105. Okay. So now I can come in here and I go equals 5,000 times sine 30, which is 0.5, divided by sine of 105, which is this guy here. And I get 2588.19. And similarly, I can do the same with the other one. So I can go equals 5,000 times sine of 45 divided by sine of 105, and I get 3,660 pounds. And then I can just remove that. So that's my final solution. So some of you are like, some of you were talking about rounding. Remember, when you guys are putting in your figures into your calculator, you will often round, right? Maybe you did sine of 45 is 0.707, sine of 105 is 0.966. Yeah, so you're already automatically carrying through some error there. That's why I like Excel. You can just carry everything through. You're not worried about transferring things into your calculator. Otherwise, you'll have to put a memory in each time. But let me just see. So if I use the trimetrics for the solutions we have to round it off. You're going to have to do some rounding, but it's close enough for me. If it's within like 1 or 2 of your final answer, then it's okay. Aniket, vector BC, yep, good one. Rusi, so if you're using graphical, then we can use to scale it down, yep. So for all problems we will be solving, would you prefer answers decimal places or significant figures? Well, decimal places is significant figures. It just depends on the accuracy to which you want to get to. So you can see here that they give the load rounded off to an integer. So it's 5,000 pounds, no decimal. The angle is an integer as well. So for me, I would be keeping to the accuracy, the level of accuracy as given by the problem. Sorry, can we please mute Shabil? Can you mute your microphone, please? Please mute your microphones, please. My gosh.
Remove them.
Okay, so that's that problem there. I think we're done for right now. Text in the sine formula, it has the sine A as the numerator and the magnitude as the denominator. Why is it the other way around this time? What do you mean? I'm not sure what you mean. I go back to, oh, over here in this problem, it's the same thing. If I flip it over, it's the same ratio, right? As long as you don't have it reversed, as long as you don't. So in this case, we're trying to work out tensions. You can see the way I did it was I had the angles on top because that's the way I've always done it. But it doesn't matter. As long as you have all the forces on the numerator and all of the angles on the denominator, or all of the angles on the numerator and all of the forces on the denominator. Yeah, as long as you're consistent. No worries, Tex. So which method would you recommend? I'd get used to all of them. Yeah, just understanding each of them. Okay. Yes, tutorials next week. Remember last week we didn't really cover that much. It was very basic. So there's no point in having tutorials unless you've learned something new. And some of the tutorials started yesterday, some of them are today, and it just doesn't give you guys enough time. But the people on Friday, they'll have something to kind of do, but not today. But I wouldn't worry about that. Tutorials will start from next week. Yeah, just before I go, there's 2 problems here. 2 problems here that I'd like to give you, and I can answer this tomorrow. Problem 2.2, so you can take a screen grab of this and put it on your computers, or you can have a look at this video again once ITS upload it. Christmas, the labs have started. No, Rohan, not next week. The labs have started. You guys, this is something that you guys need to be aware of. You need to check the Moodle shell. I'm not sure whether you guys are getting the emails, but when I post something in Moodle, it should get delivered as an email. I don't know whether that is the case, but you should have an alert in your email that says, hey, Dan has posted something to Moodle shell. Now, I think I was pretty clear. Have you guys taken a screen grab of this?
Yes, sir.
Okay, great. So you guys can attempt these problems and I'll come back and answer them in the next session. Okay, but I want to be clear that I have, you know, I've been getting a lot of private messages in Viber, and that's okay. I don't mind doing it, but there's 300 and something students enrolled in this course, right? So, you know, it would be really helpful for me if you paid attention to what comes up on Moodle. So here is the Moodle shell. Now you'll see the announcement up here. Hi team, labs roll. You can download the videos and start immediately. Please attend your designated lab sessions for Q&A. Watch the videos and have VDAS installed prior to your lab session. If you can't install VDAS, right, if you've got a problem, alert your lab demonstrator and they might be able to help you, either help you download it, or the other thing is they can, you can go through the actual experimental, the simulation in the lab session. You can see here, tutorials will start in week 3 once we've covered week 2 material. Okay, and then it says, please attend my lectures because I like the company. Now, if you want to go down, you'll notice if you come down to the lab session area, you'll see the Zooms right up the top for the lab session that you're a part of. You'll see the lab reporting writing guide, the marking rubric. You'll see the lab manual for my labs, labs 1 to 3. And then you'll see the videos that I did. And please forgive me, I'm an amateur, right? I'm not a YouTube star or anything like that, but I've done some videos that may be able to help you better understand some of the theory and also how to operate VDAS. Okay, so download those videos. I think the longest one is 20-something minutes. Okay, that has a bit of theory in it, but have a go at that, right? So you can better understand it, and then turn up to your lab session so that you can ask some questions. Yeah, Kunal, the lab sessions, the lab report is done individually. Huh? What about us who lab? Well, if they're cross-credited, Nitesh, you know, sort that out with Jay. That's not my area. I'm not the course coordinator. Jay would be the one to speak that through with him. Yeah, Kunal, labs are done individually. Great, Nikhil. Link of Viber group, please. I think it's here in the Moodle shell. But if you come up here, I thought it was, did someone do, I'm pretty sure it was up here, right? Where was it? I thought I saw it here. I think if you go, let's have a look at these announcements. There we go. So if you go to the 18th of August, you can see the Viber group link here. Okay. Nicole, the link for VDAS is it's here, right? It's at the bottom of labs. So if you come down here, that's the link. Okay, so if you click on that link, it'll take you to the VDAS download. Yep, Nikhil, so what? Yep, no worries. So what labs? So when will labs be due? I think it's usually due the week after. Let's just sort that one out. Technically, you can do all 3 labs like today and you'll be done. Mark, what's your question, mate?
So if we miss this lab, can we fit in the other lab as well?
I really don't see a problem with that, okay? But if you've signed up for a lab session, just try and attend the lab session that you've signed up for, okay? But jump on another one if you've missed one. That's fine. Yeah, Aniket, okay. Go, mate. This is just optional. I'm not holding anyone hostage here. Okay, guys, thanks for your time. I'll see you guys tomorrow. See you later.
Thank you, sir.
No worries, guys. See you tomorrow.
Thank you, sir.
Naka.
Thank you, sir.
Recording stopped.
Hey, thanks, ITS. Appreciate it, mate. You can end this meeting if you want.